X-rays are electromagnetic waves with extremely short wavelength measured in orders of angstrom. In numerous applications fields, X-ray is now widely used. Medical applications make extensive use of X-ray equipment. The use of X-rays extends to non-destructive inspections, including detecting minute cracks in pipes and luggage checking at airports. The CT scanner makes use of X-rays. Here, CT stands for computed tomography. A position-dependent image parameter is used to construct the image. The image parameter in a CT scanner is the X-ray absorption coefficient. In a CT scan, the X-ray passes through various kinds of tissues and bones with different X-ray absorption coefficients. The grayscale image is created using the X-ray absorption coefficients of the pixels in the image slice. So, although computer is used to calculate the X-ray absorption coefficients using the intensity of transmitted X-ray along the slice, X-ray functions play the most significant role in CT. People are worried that X-rays could harm the human body. As a result, the word X-ray is dropped from the name X-ray CT, thus in favor of CT. In this presentation, we will investigate how the X-ray is used in the CT scanning. Now let us see how the X-ray is generated. An X-ray is a type of electromagnetic wave with wavelengths ranging from 0.01 to 10 angstrom. In materials, the intermolecular distance is on the order of angstrom. The inside of materials can be examined using X-rays. So X-rays are now commonly utilized in airport baggage inspections, non-destructive tests on X-ray CT, computed tomography, DNA structure analysis, and X-ray diffraction, and so on. Well, this shows X-ray generation setup. So this basic setup for producing X-rays is shown in this figure. The target metal is exposed to a high positive voltage, which attracts hot electrons generated by the filament, so electron gun. So electrons from electron guns are accelerated due to the high voltage applied at the target. When these electrons collide with target metal here, X-rays are generated. This figure depicts molybdenum target's X-ray spectrum. So if we use target metal as molybdenum, then you can get the X-ray of this kind of spectrum. Two spectra. The continuous spectrum starting from lowest wavelength here, from the minimum, just continuously changing wavelength, and two characteristic peaks, this one, are combined in this figure. So the continuous X-ray and characteristic X-ray is called continuous X-ray, and these peaks are called characteristic X-ray. Are the two types of X-rays. Different mechanisms produce these two kinds of X-rays. If you use low voltage, that's not low, but relatively low or high voltage, so 10 kilovolt and 15 kilovolt and 20 kilovolt. In that cases, we have only continuous X-rays. Okay. However, if you use 25 kilovolt, then we have characteristic X-rays with continuous X-rays. So low voltages below 25 kilovolt, we have only continuous X-rays. However, if you use 25 kilovolt and above, then we have characteristic X-rays in addition to continuous X-ray. Okay. This person is Wilhelm Röntgen. He first discovered the X-ray. And this figure is first X-ray photo of the bones in his wife's hand and her wedding ring in 1895. And he won the first Nobel Prize in physics in 1901. Now let's see a mechanism of continuous X-ray. Bremsstrahlung, which means braking radiation or deceleration radiation, produce the continuous X-ray. Electromagnetic radiation is produced when high-speed electrons are decelerated by the target metal. During the interaction with nuclei of target metal material, high-speed electrons, these electrons, lose energy. Okay. This lost energy is emitted in the form of an electromagnetic wave, that is X-ray, as shown in the figure. Electrons interact with metal nuclei in a variety of ways. Okay. Metal nuclei bend some electron somewhat. So little band. Some electrons, on the other hand, lose all of their energy and come to full stop here. Some electrons will be bent in this way, or even more, and some electrons will just pass through the target material. Okay. So electrons interact with the metal nuclei in various ways. Therefore, continuous X-ray is produced since this energy lost by electrons in the presence of in the process of interaction with the metal nuclei is continuous. So continuous interaction. So we can have the X-ray of continuous wavelength. Okay. Since the lost energy of electrons, this electron delta E, is emitted by electromagnetic wave X-ray. So the energy of X-ray is then given by this lost energy of this electron. Okay. So the wavelength of the emitted X-ray can be calculated as follows. So from the equals C. So the wavelength of the X-ray emitted is given by this equation, and here delta E is the energy lost by this electron due to the interaction with the electrons in target material. Actually, interaction with the target material. At voltage of V, if we use voltage V, electrons have an energy of EV. E is the charge of the electron. When electrons completely stop interacting with the metal nuclei, an X-ray of the lowest wavelength is produced. Since the energy lost by the electron is largest, so in that case we can obtain the X-ray of the lowest wavelength. The total energy of the electrons in this situation becomes the energy of an X-ray. We can observe that by plugging this energy. This is energy of electron from the electron gun at the voltage of V, as EV, right? So this becomes the energy of X-ray, so we can get the lowest wavelength of an X-ray is given by this equation. This is lowest X-ray wavelength produced. So in here, delta E is EV. Okay. So we can get this relationship. Here, the unit of the wavelength lambda minimum is Armstrong, and the voltage V, unit of voltage V is 1000 volt. Okay. So we can observe that the continuous X-ray's lowest wavelength is determined by the voltage given to the target material, not the target material itself. So this lowest X-ray wavelength only depends on the voltage applied, not depend on the material, target material. So it only depends on the voltage applied to the target metal. Now let's see the characteristic X-ray. The characteristic X-ray is produced when electrons from the electron gun interacts with the electrons in the target metal. Okay. The target metal's K-shell electrons are expelled by incoming electrons, which then fill the K-shell with electrons from the upper cell. So electrons from electron gun interact with the electrons of target metal, and this electron expelled the electrons in K-shell. So K-shell is removed. Then the electrons in the upper cell fill the vacant position in the K-shell. Okay. So in this process, energy is released as an electromagnetic wave, which is the characteristic X-ray. If the electron in the air cell fills the K cell, so here, electrons in the K cell, air cell, fill the K cell, the X-ray is referred to as K alpha line. We call this X-ray K alpha line. On the other hand, if the electron in M cell, it's a little higher energy level, M cell, fills the K cell, that X-ray is referred to as K beta line. Okay. So each metal has its unique set of energy levels. As a result, the characteristic X-ray is determined by the target metal. The continuous X-ray doesn't depend on the target metal. It depends on only the voltage applied, but the characteristic X-ray depends on the target metal. Each target metal has different energy levels. The energy levels of tungsten, there's tungsten energy level, and the molybdenum energy level are given here. The wavelengths of the characteristic X-ray of tungsten are substantially shorter than those of molybdenum, as can be shown here, because energy level is wider in tungsten compared with that in molybdenum. So energy levels difference is smaller here and larger here, so we can have a shorter wavelength of X-ray here using tungsten. Okay. This table shows the K alpha and K beta line of the target metal. Yeah, the wavelength. This wavelength is characteristic X-ray wavelength, and the wavelength of metal targets with larger atomic numbers becomes shorter. You can see here. A large atomic number target metal is shortest. Yeah. And chrome, K alpha line is 2.29 angstrom, but for a heavy metal tungsten, K alpha line is much shorter, 0.021 angstrom. So generally, wavelengths of metal targets with larger atomic numbers become shorter. Okay. Now let's see the X-ray tube. So this figure depicts the structure of an X-ray tube. All of the components are kept at the vacuum of 10 to the minus 7 torr inside Pyrex glass tube. So X-ray tube is made of Pyrex glass tube, and inside here should be maintained at the vacuum of the 10 to the minus 7 high vacuum. Electrons is emitted here, filament, and accelerated to the metal target by the high voltage applied here. So if there is some gases here inside, then these electrons collide with the gas molecules, and the speed will be reduced. So we have to maintain inside vacuum tube a high vacuum, about 10 to the minus 7 torr. Otherwise, electrons here interact with gas molecules, and we cannot produce the X-rays. There are two kinds of X-ray tube. One is fixed anode X-ray tubes, and the other is rotating anode X-ray tubes. This is a rotating anode X-ray tube. In a fixed anode X-ray tube, the target metal, this anode, is fixed, whereas in rotating anode X-ray tube, the anode can be rotated by induction motor. So this rotator will rotate the anode. Okay. The structure of a rotating anode X-ray tube is shown here. This one. The target metal, the anode, the rotating anode, revolves at around 9,000 revolutions per minute, and the rotating anode X-ray tube, very high speed. A rotating anode X-ray tube has a substantially longer lifespan than a fixed anode X-ray tube, because electrons beam hits the different position with each turn. since anode is rotating, so electron beam will hit the anode target metal different position each turn, because this is rotating. This picture for the X-ray tube. This is metal target here, anode, and there is induction motor, and this electron gun filament. Electron is produced by heating this filament, and X-ray will come out through the window. Okay. This picture shows the fixed anode X-ray tube. Size is very small. The length of the pan, so about less than 20 centimeter. So this is a fixed anode X-ray tube. The target structure can be seen in this figure. So if you see here, this is anode, and target metal is represented as gray region, this region, and the slant is made where electrons collide with the metal target. So there's some angle here, so 18 degree, 16 degree, and 12 degree slant angles are frequently utilized. When a smaller slant angle, 12 degree and 20 degrees, a much more focused X-ray is produced. Okay. The filament's electron beam, electron gun here, should be focused on the target metal's slant region, this region. Collimator, this one. A collimator warps around the filament, okay, controlling the spread of the electron beam. There are two different selectable grooves on the collimator. So you have generally two selectable grooves. The electron beam is more focused on the target metal with a small groove than with a large groove. You can see here, if you use a small groove, you can have more focused electron beam. You can see here the difference here. The most of X-ray beams are emitted through the X-ray tube's window, this window. However, some beams can leak in unexpected directions, so this direction. But this figure are exaggerated, because most of X-ray beams are coming through this window. But some of small part of X-ray might go this direction or this direction. So this figure is much exaggerated. The people in the vicinity of X-ray tube are at risk from this leakage X-ray. The X-ray tube is mounted inside a lead shielder as shown in the figure. So lead shielder, this one, to observe this leakage X-ray. This fielder serves as a leakage X-ray observer as well as a protector for the fragile glass X-ray tube. So X-ray tube is made of glass, so we have to protect this X-ray tube, very fragile. So this shielder also protects this fragile X-ray tube. In some cases, we will need to know the exact wavelength of the X-ray. In the X-ray diffraction experiment, for example, the exact value of the X-ray wavelength is required to measure the interlayer distance. For the baggage inspection at the airports, we don't need the exact wavelength of the X-ray, so we just use the continuous X-ray. However, for X-ray diffraction experiment, we need the exact wavelength of the X-ray. So X-ray filtering is utilized in this case. For this, the K line of the characteristic X-ray is commonly used. The K alpha 1, K alpha 2, and K beta 1 lines are the most intense of the K lines. So in this figure, we have just shown the K alpha line and K beta line, but if we enlarge this figure, we can see K alpha 1 and K alpha 2 lines. Okay. However, K alpha 1 and K alpha 2 cannot be distinguished in X-rays of some metal targets. So in this molybdenum target X-ray, we can distinguish K alpha and K beta, K alpha 1 and distinct K alpha 1 and K alpha 2, but in some cases, some metal targets, we cannot distinguish K alpha 1 and K alpha 2. In most cases, K alpha 1 is twice as powerful as K alpha 2, as shown in this figure. So K alpha 1 is much larger than K alpha 2. In comparison, K alpha 1 is 5 times more powerful than K beta 1. So K alpha is much powerful than K beta. Therefore, K alpha 1 lines are commonly utilized. Okay, this line. Materials X-ray absorption is wavelength dependent. So X-ray absorption depends on the wavelength of the X-ray. There is a specific absorption edge wavelength for each material. So this absorption edge, the material is transparent to X-rays with wavelengths longer than this wavelength. So for the X-ray of wavelength longer than this absorption edge, the material is transparent, right? X-ray is transparent, right? When electrons in the K cell of filtering material are excited by an X-ray with a wavelength larger than absorption H wavelength, the electrons emit an X-ray with the same wavelength as the incident X-ray when they return to ground state. When this occurs, it is referred to as transparency. So, the electrons in a K shell of the filtering material are excited by an X-ray whose wavelength is longer than this absorption H. Then the electrons emit X-ray of wavelength, the same wavelength of the incident wavelength. So that means transparent, right? So if the wavelength is of X-ray is longer than this absorption H wavelength, then the material is transparent. X-ray is transparent. Okay. As a result, the filtering material absorbs X-rays with a wavelength less than the absorption H wavelength, while remaining transparent to X-rays with a wavelength larger than absorption H wavelength. So in this wavelength, the material that's the filtering material observe the energy of X-ray, but above this wavelength X-ray, the filtering material re-emit the same X-rays of incident X-ray. So it means that filtering materials are transparent for this longer wavelength X-ray. Okay. If we utilize a filtering material with absorption H wavelengths near the K alpha line of an X-ray source, the filtering material can only emit the K alpha line, while the others are observed. Right? The wavelength dependence of nickel's absorption coefficient is shown in the figure. This is nickel. The absorption H wavelength of nickel, this filtering material nickel, is roughly 1.5 angstrom. Okay. So the copper's K alpha line is around 1.5 angstrom, which is close to the absorption H of the nickel, which was shown in the previous slide. So copper's K alpha line is near to the nickel's absorption H wavelength. So this absorption line of the nickel. So no filter. If we use filter, this blue line shows the absorption curve for the nickel. As a result, nickel can be utilized as filtering material for copper targets X-ray source. This figure depicts X-ray filtering. By passing the copper targets X-ray through nickel, we can see that only K-alpha line is emitted. Okay. K-alpha, the intensity of K-alpha line also reduced, but the K-beta line is completely reduced. You can see, right? So we can use this K-alpha line. Then we know the exact wavelengths of this X-ray. This table shows filter material for each target material. For modern target X-ray, we can use zirconium filter material and copper, nickel, and chrome, iron, mangan, cobalt, iron. So for this target material, we can use filtering material. Right? And the X-ray for this target material, the ratio for K-alpha and K-beta is given here. So K-alpha line is 5 times or 7 times, 9 times intensity is larger than that of K-beta line. And this column shows the filter thickness for reducing the K-alpha and K-beta intensity ratio is 500. So if we use 0.12 millimeter zirconium filter material, then K-alpha line, the ratio of K-alpha and K-beta is 500. So K-beta line is nearly completely reduced. So we can have only a K-alpha line. Okay. This column shows the intensity ratio of instant K-alpha line and transmitted K-alpha line. So 0.29 means the transmitted K-alpha line is has the intensity of 29% in intensity of that of intensity of instant line. So 71% of intensity is observed by the filtering material. So this shows the ratio of the transmitted K-alpha line intensity and to the instant K-alpha line intensity. Now let's see the X-ray detection. We can use detection, the scintillation detector for X-rays or radioactive activity. So radioactivity and X-ray can be used by the same detector. Okay. So X-rays and radioactivity are detected using the scintillator. Okay. When high energy particles or electromagnetic waves interact with a scintillator material, this material emits visible or ultraviolet light. NAI is a common scintillator with a long history of use. However, ceramic materials A photomultiplier tube is in contact with the scintillator to amplify the photons released by the scintillator. So this is photomultiplier tube, and this is scintillator material. A gradually increasing voltage is applied to the electrodes of the photomultiplier tube. So it's gradually increasing voltage is applied to the electrodes. The emitted photons collide with the photomultiplier tube's first electrode. So high energy particle or light is instilled into the scintillator material. Then visible light or ultraviolet is emitted, and this light collides with the first electrode here. Then photoelectric effect causes electrons to be emitted during this interaction. So photoelectric effect gives the electrons that's coming from the metal electrode. At higher voltage here, the first higher voltage here, 200 volt, these photoelectrons are accelerated to the second electrode. Then the secondary electrons are emitted when electrons collide with the electrode's metal surface here. So second electrons are emitted by the colliding of electrons to the metal surface. Depending on metal used as electrode, the number of secondary electrons per instant electron is usually 2 to 10. In this figure, we used the number of secondary electrons, just 2. So one electron is entering to the electrode, and then 2 secondary electrons are emitted, and then 2 secondary electrons become 4 secondary electrons. In this way, number of electrons are increasing. So the number of secondary electrons increases geometrically as electrons move to the successive electrodes at increasing voltage, and the electrons are finally measured as a current at the output. Yeah. If the number of electrons at each electrode is doubled, so it is 2, then the output of the photomultiplier with 10 electrodes will detect 2 to the 8, thus 256 electrons per input photon, as shown in the figure. So this scintillator unit is used to detect X-ray and radioactivity.